Now let's look in a little more detail at what's going on in this acid-base neutralization reaction. So here's the reaction that we've seen before. Hydrochloric acid. Remember, hydrogen chloride is a gas, but when you dissolve it in water, when it's aqueous, it becomes an acid because, according to Arrhenius, it's going to give you H plus ions. So when this acid reacts with the base sodium hydroxide, we make a salt, sodium chloride, plus water. And a salt is just an ionic compound that is the product of the reaction between an acid and a base. In particular, it's a strong acid and a strong base, and we'll talk about what that means in just a little while. So let's think about what's going on in this reaction. So we're going to imagine then that when you dissolve this into water, that these ions all come apart. So this equation right here is sometimes called the molecular equation. So I'll just abbreviate that molec. So the molecular equation, because it's showing all the species as molecules. Now we know that ionic compounds don't exactly form molecules, so these are more like formula units, but that's okay. So this is the molecular equation. And now what we're going to do is we're going to ionize everything that could possibly ionize in solution. So hydrogen chloride, because it's an acid, it's going to come apart to give us H plus ions. And those are dissolved in water, so we're going to write AQ next to that. So if there's an H plus, where did that come from? Well, it came from this HCl dissociating or breaking up. And so we're going to form a Cl minus that is also aqueous. Alright, so what about the sodium hydroxide? Well, in water, sodium hydroxide is a strong electrolyte. That means it's going to break apart into its ions. It's going to dissociate. So we end up with sodium cations, aqueous, and hydroxide anions. Oops. Also aqueous. And so now when the reaction happens, what do we have? Well, NaCl can again break up, so we've got sodium cations because NaCl is also a strong electrolyte, like we've discovered. So Na plus Cl minus, aqueous. So in this reaction, the other product, water, well, water is the solvent, so it doesn't make sense to say that it is aqueous. Water dissolved in water doesn't make any sense. So we write L to indicate that it is in its liquid state. And water is not going to ionize. Remember, it is not an electrolyte. If we test it with a light bulb apparatus, it does not cause the light bulb to light up. It is not an electrolyte. So we're just going to leave it together like this, H2O. Okay, so this form for the equation where everything that can possibly break up into its ions does, and we write it that way, is actually probably a better representation of what is actually going on in the solution. We've got these individual H plus ions, these individual chloride ions, the sodium cations, and the hydroxide anions. They're all floating around in there. And then when the reaction takes place, what happens? Well, this H plus hooks up with this hydroxide, and they turn into water molecules that then do not come apart. So this is sometimes called the overall or complete ionic equation. So the overall ionic equation. EQN is my abbreviation for equation. So overall or sometimes complete ionic equation. You'll hear it both ways in different places. So this is showing you what things might actually look like in solution, floating around like this. Now you'll notice if we look at this arrow that we've got sodium cations here on the reactant side of this reaction, and they're also over here on the product side, and they've been unchanged. Nothing has happened to them at all. So, well, why don't we take them out of the equation since they're not really involved in the interesting chemistry. In fact, chemists call these guys spectator ions because they just sort of watch the reaction happen. So I've circled what we call spectator ions. So can you see any other spectator ions that are in this reaction? Yeah, here's one. Chloride on the reactant side is not changed when we see it over here on the product side. Now hydroxide and H plus are because we don't see them over here on the product side. So chloride and chloride then is another spectator ion. So now what we're going to do is a little trick. We're going to imagine that this were an algebraic equation and this were an equal sign between two sides of an algebraic equation. And what we can do is subtract sodium plus from both sides of our equation. So we can effectively cancel that out. So we subtracted sodium from both sides. Now this reaction is still balanced because I've done this to both sides of the equation. Now what I'm going to do is subtract chloride, minus Cl minus, minus Cl minus, from both sides of this reaction. and that cancels out. So now what we're left with are just the things that are actually reacting chemically. And this is useful for chemists because it shows us really what the essential reaction is, so that we can think about it more clearly without all the shrubbery being around. So H plus then reacts with OH minus to yield water, H2O. And this is the essential chemistry of a neutralization reaction. And once we've canceled out all these spectator ions, the equation that we end up with is called the net ionic equation, because we're just including the specific ions that are actually reacting in some way. And now we can see why this reaction happens. So we sometimes call this a driving force. So the driving force for this reaction is taking ions out of solution. How do we do that? By forming something that is no longer an ionic compound. In this case, it is water. So we're taking these ions out of solution so that they're no longer dissociated into something that will not dissociate. In this case, a molecular compound that doesn't dissociate in water. So water is a non-electrolyte. It will not dissociate in water. And so that's all about overall ionic equations, molecular equations, and net ionic equations. And we can write these for any kind of acid-base reaction.